Imagine if nothing you've ever done, no glance, no breath, no quiet thought whispered only to yourself, has truly vanished. Physics suggests it may be so. From the faint afterglow of the Big Bang etched across the sky to the tracks of cosmic particles passing silently through stone, reality itself seems to keep a ledger far deeper than memory and far older than history. Black holes may guard secrets instead of swallowing them. Deserts hold glass born of ancient fire. Even our machines now catch whispers of the universe's first seconds. What if your life is already inscribed in this vast archive, scattered across dust, light, and time? Journey with us into hidden experiments, lost tapes, cosmic signals, and fragile quantum states to explore a haunting possibility that every moment you've lived may still exist, written into the quiet fabric of space-time itself. When people first hear the idea that memory might exist beyond the fragile tissue of the brain, the thought seems almost impossible, like a story whispered by dreamers rather than scientists. Yet when you pause and listen closely to the quiet language of the universe, you begin to sense that every step, every gesture, every flicker of thought may leave some trace beyond the boundaries of a single life. Physicists have long suspected that the fabric of reality itself, what we call space-time, is not a blank sheet but a kind of silent ledger. It does not speak, yet it keeps everything. A raindrop sliding down a window pane, a hand lifted to wave across a crowded street. Even the heat left behind by your own body as you pass through a room. Each moment changes the field ever so slightly, and those changes never entirely vanish. More than a century ago, when Albert Einstein was working in Zurich and later in Berlin, he began to reshape the way we think about time and space. In 1905, and then again in 1915, he described a universe where the past and the future are not erased and created anew, but instead lie together as parts of one vast whole. He called the structure spacetime, and in doing so, he helped scientists imagine that every event, from the swing of a pendulum to the light of a distant star. Later thinkers would call this the block universe, a picture where the entire timeline of the cosmos already exists, not rolling out like film through a projector, but present all at once, frame after frame held in a single reel. If that is true, then memory is not just in our heads. It is somewhere deeper, woven into the geometry of reality. To understand why this matters, imagine walking across a wooden floor in an empty house. Even if you tiptoe, you leave faint impressions. A creak here, a shiver of dust there, air stirred in invisible curls. The universe is much the same, but on a scale so vast it feels sacred. Physicists speak of world lines, the invisible threads drawn through space-time by every object as it moves. Each world line is a record. Each particle writes its own story as it goes. When a bird cuts through the air on a cold January morning, when the planet Mercury slides around the sun, when your grandmother lifted you for the first time, those motions and the fields they disturbed still exist as patterns in the whole. This idea unsettled many thinkers when it first appeared. Henry Bergson, the French philosopher, argued fiercely against Einstein in 1922. Insisting that lived time could not be frozen into a diagram. Einstein, ever calm, answered that while human experience flows, physics shows something still. The distinction between past, present, and future is only a stubbornly persistent illusion, he once wrote in a letter. After the death of his friend Michel Basseau, too, him it was comforting the idea that somewhere the moments of laughter and sorrow, the faces of loved ones, were not gone but still inscribed in the structure of things. Modern physics has built on this vision rather than abandoned it. Relativity tells us that the sequence of events depends on where you stand and how you move, but the full tapestry remains untouched. It is as though we are tiny insects crawling across a mural so large we can never see the whole, yet the paint has already dried. Some scientists use the metaphor of a ledger because it is quiet but exacting. Every force exchanged, every photon emitted, every tiny jolt of heat is accounted for. None of it slips away without a trace. You can feel the weight of this when you consider the night sky. Light from the Andromeda galaxy left its stars 2.5 million years ago and travels still. carrying with it an ancient message about what once was. When that light reaches our telescopes on a crisp autumn night, it is not a ghost. It is an intact report from a time before humans carved words into stone. The path of each photon is part of the memory of spacetime. It cannot be undone. Some of the most delicate experiments of the 20th century were, in a sense, attempts to peek into this cosmic archive. Michelson and Morley failed to find an ether, but their work set the stage for Einstein's insight. Later, the bending of starlight measured during the 1919 eclipse off the coast of Africa proved that gravity could shape the path of light, meaning spacetime was no silent void, but an active participant in the story of the universe. Each bending, each delay, each shift in wavelength is a permanent mark, even though the language of physics can feel cold. There is something deeply human about this vision. It says that the moment you looked up at the sky on your birthday, the air you moved through, the photons you scattered, the warmth you gave off, all of it joined the record. It will not be erased. You might forget. Your brain may lose the memory, but the universe will not. We are patterns written across a page we cannot turn, but we are there nonetheless, as we step into later chapters. We will meet experiments and discoveries that make this idea less abstract, black holes fighting to keep their secrets. Light trapped since the dawn of time, deep ice remembering long winters before cities stood. For now, it is enough to stand at the edge of the thought itself, that behind the everyday rush, reality may be one vast, unbroken memory. And we are walking stories written into spationing, in the quiet shops of old European towns, where brass gears and polished glass once filled the workbenches of patient craftsmen. The heartbeat of time was built piece by piece. Imagine a watchmaker in Geneva in the winter of 1714, leaning close to a candle's glow, adjusting the balance wheel of a pocket watch that might outlast its first owner. In those rooms, time seemed simple and obedient, measured in steady ticks and swinging pendulums. It was the age of Isaac Newton, and to Newton, time was as absolute and smooth as the polished brass in a clock's movement. He wrote of it in the Principia Mathematica in 1687, describing a universal time that flowed equably without regard to anything external. This view suited the age of sails and stars, when British shipbuilders and the Greenwich Observatory tried to tame the oceans with accurate chronometers and clear tables of celestial positions. For centuries, this vision of time as an invisible river flowing steadily forward served explorers, kings, and merchants. Clocks left English ports on voyages of discovery. Dutch traders set their hourglasses by them. French mathematicians calculated eclipses and tides with confidence that seconds and hours were the same everywhere. The metaphor was easy to picture. A single great clock set by the Creator, ticking for all. Even when men like Christian Huygens and John Harrison fought to build more accurate timepieces. Huygens with his pendulum clocks in 1656. Harrison with his marine chronometers winning the British Longitude Prize in 1765. The idea behind their work was never challenged. Time was there first. The watches only tried to follow it. Yet beneath that quiet belief, cracks were forming. By the mid-1800s, telegraph wires crisscrossed continents and railroads demanded schedules. More precise than church bells and local noon could give, people began to notice that clocks did not always agree, and signals arrived at odd intervals depending on where and how they traveled. The world was shrinking, and with it, the certainty of Newton's absolute flow. By the time Albert Einstein was born in Ulm, Germany, in 1879, the need for a deeper understanding was already stirring. His early work at the Swiss Patent Office in Bern put him close to a culture obsessed with precision. Switzerland's watchmakers had long been famous, and trains and factories ran on strict timetables. It is easy to picture the young Einstein glancing at clocks in shop windows as he walked home at night, wondering if their ticking told the whole truth. In 1905, while working quietly and largely unknown, he published a paper that broke the smooth river of time in two. Special relativity said that time could stretch and contract depending on how fast you moved and where you stood. Two clocks, once thought to be faithful twins, could drift apart if one traveled close to the speed of light. The old dream of a single universal time dissolved into a world of shifting perspectives. 10 years later, in 1915, his general theory of relativity went further still, showing that gravity itself could bend time, making it pass slower near massive stars and faster in the emptier reaches of space. No master watchmaker could build a clock to rule them all, because time was not a thing apart. It was part of the weave of space itself. From these ideas grew a picture that felt both wondrous and unsettling. Instead of a flowing present sweeping the past away, relativity described a four-dimensional structure where past, present, and future all coexisted. Hermann Minkowski, Einstein's former mathematics teacher, had introduced this geometric vision in 1908, declaring that henceforth space by itself and time by itself would fade into shadows, and only a kind of space-time would remain. In this block-like universe, the path of every star, every atom, every heartbeat could, in theory, be laid out from birth to death like a thread inside an enormous tapestry. What we call now was only one thin slice through something far larger, to a world raised on the ticking certainty of clocks. This was hard to accept. It meant the comfort of believing the past was gone might be an illusion. It suggested that the moment you blew out birthday candles or stood at a graveside still exists, fixed within the great map of space-time. Einstein himself, though often portrayed as cool and detached, felt the weight of it. In March 1955, just weeks before his death, he wrote to the family of his lifelong friend, Michel Besso, saying that Besso had merely preceded him a little into another part of this grand structure, and that for us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. The culture of timekeeping adapted but never quite recovered its old certainty. Railways and telegraphs became GPS, satellites, and atomic clocks. And while these tools work because they use relativity rather than defy it, the old dream of a single universal second ticking everywhere has gone. Even the antique clocks in Swiss shop windows seem to keep time only for their owners, while somewhere above them, satellites adjust constantly to account for the bending and stretching of time by Earth's gravity and speed. This journey from Newton's quiet flow to Einstein's restless geometry is often called a revolution. Yet it is also a reminder of how deeply human minds crave stability. We want time to march in step like a regiment on parade. Einstein showed instead that it drifts and bends. Yet in doing so, he also revealed a deeper stability, the entire history of the universe present all at once, as if engraved. It is this vision, this watchmaker's paradox, that sets the stage for thinking about memory, not just as something inside our heads, but as something the cosmos itself may hold. The old clocks still tick, but behind their brass faces lies a silent and immense record, where nothing truly slips away. When the story of reality moves from the great sweep of clocks and stars into the strange quiet of the subatomic, it feels at first as though we are stepping into mist. The world we know, with rails and timetables and pendulums, seems to fade behind us, and in its place there is a dim field where particles flicker in and out of sight, trading signals that no instrument can catch in flight. Here in this fog, the idea of connection takes on an uncanny shape. Physicists call it quantum entanglement. And though the term now lives in science books and casual conversation, its heart still beats with wonder and unease. It says that two particles born together, electrons spinning opposite ways, photons springing from the same burst of light, can remain bound, no matter how far apart they travel. Touch one, and the other seems to know instantly. As if space itself were not a barrier. Albert Einstein himself disliked this notion so much that in 1935 he joined Boris Podolsky and Nathan Rosen in writing a paper at Princeton, arguing that quantum theory must be incomplete. The famous EPR paper, as it came to be known, described what Einstein called spooky action at a distance. He could not accept that nature allowed such silent signaling faster than light, because relativity had told him that nothing outruns that cosmic speed limit. Niels Bohr, working in Copenhagen, and so often Einstein's sparring partner, pushed back, insisting that the mathematics of quantum mechanics, strange as it was, kept matching experiment after experiment. The two men debated through letters, lectures, and conferences, their arguments echoing through the decades like distant thunder. Einstein believed hidden variables, unknown gears behind the fog, must explain the apparent link, while Bohr held that the link was fundamental. For years the question stayed philosophical, since there seemed no way to test it directly. Then, in the early 1960s, a young Irish physicist named John Bell, working quietly at CERN in Geneva, devised a way. Bell's theorem, published in 1964, offered a precise test to decide whether any hidden variable theory could reproduce the predictions of quantum mechanics. If you measured certain properties of entangled particles, their polarizations or spins, and the correlations exceeded a strict limit, then no local clockwork explanation could hold. The universe itself would be non-local in some deep sense. Bell's equations were abstract but clear, and they gave experimentalists a target. By the 1970s and early 1980s, experiments began to rise to that challenge. In 1982, Ailing Aspect and his team in Orsay, France, used fast switches and polarized photons to test Bell's inequalities under conditions that closed many of the old loopholes. The results came back leaning unmistakably toward the quantum side. The correlations were too strong, too precise, to be explained by any signal traveling at or below the speed of light. The eerie connection Einstein disliked seemed real. Since then, refinements have tightened the net. Experiments in Delft in 2015 using distant electron spins, work at MIT and Vienna closing detection gaps, all telling the same quiet story. Entanglement is not just a quirk of equations, but a feature of the world. This matters for memory and for the idea that nothing is ever truly lost. Because entanglement is not just about strange instant responses, it is also about information. Quantum theory tells us that information is the deep pattern describing a particle's state, cannot be copied perfectly, but also cannot be destroyed. A photon's polarization or an electron's spin may shift, spread, or mingle with its environment, but the full information is conserved in the total wave function. Stephen Hawking once suggested black holes might swallow information forever, their event horizons acting like cosmic shredders. But later work, much of it tied to thinkers like Leonard Susskind and Juan Maldacena, pushed back, showing that even there, quantum mechanics seems to keep the books balanced. The term quantum information can't be destroyed is not poetic exaggeration, but a hard rule. The equations do not allow erasure. One way to picture this is to think of two dancers starting in perfect step in a dark room. Even if fog rolls in and you can no longer see their feet, the steps remain linked. If one lifts a left foot, the other must answer with a right to keep the dance whole. Now, scatter them across the world, and still their rhythm matches. The dance floor is the universe itself, and the fog is our ignorance. The beat continues, whether we watch or not. At first, these ideas were discussed in the quiet back rooms of physics conferences, but over time they have reshaped entire fields. Quantum computing depends on entanglement to link qubits in delicate states that hold and process information far beyond the reach of classical bits. Quantum cryptography promises unbreakable codes, because any eavesdropper would disturb the fragile entangled link and reveal their presence. And deep in the mathematics that describe black holes and expanding space, entanglement appears again, suggesting that the fabric of spacetime itself may be stitched together by webs of quantum information. Yet, for all the modern devices and technical words, the feeling behind this discovery remains strangely human. To know that two particles, once neighbors in a flash of energy, can remember each other across light years is to feel that the universe is not a cold void, but a kind of silent witness. When aspects detectors clicked in that French lab in 1982, they were registering something more than a number. They were catching the whisper of connection that Einstein doubted, but that the cosmos seems to insist upon it. Also hints at why memory might be larger than the self. If the smallest building blocks of matter refuse to forget their shared past, if their properties stay written into the whole, even as they drift apart, Then the idea that our own moments might leave some deep trace no longer sounds entirely mystical. Quantum mechanics does not offer a map of personal memory, but it shows that the universe is careful. It keeps accounts even when we cannot read them. And somewhere in the fog, the echoes of every interaction still hum. Waiting for the right questions to bring them into the light, in the spring of 1935, in a quiet office at Princeton, Albert Einstein sat with two colleagues, Boris Podolsky and Nathan Rosen. And together, they launched what would become one of the most haunting expeditions in the history of science. They were not boarding a ship or setting out across mountains. Their journey was through the structure of reality itself. A trek into the invisible and the untested, where logic was their only compass. The paper they produced, published in the Physical Review that May, was dryly titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" But its effect was anything but mild. In those careful pages, they challenged the rising faith in quantum mechanics, declaring that the new physics, dazzling as it was, left something vital unexplained. Einstein had long admired the precision of quantum theory, but distrusted its heart. He had built much of the early foundation himself. His 1905 paper on the photoelectric effect helped prove that light came in quanta, yet he recoiled at the idea that nature could be governed by pure chance. God does not play dice with the universe, he told colleagues, an objection as philosophical as it was physical. Podolsky and Rosen shared his worry that quantum mechanics offered predictions without describing the deeper machinery behind them. The three men set out to show, using a thought experiment, that if quantum theory were correct, then the world must allow something profoundly unsettling, influences leaping across space. Faster than any light could travel, their imagined scene was simple but sly. Take two particles that once interacted, say two electrons sprung from the same event. According to quantum mechanics, their properties would be tied, yet once separated, each could be measured independently. Measure one's momentum, and you would instantly know the others, no matter how far apart they had traveled. If the universe respected Einstein's own theory of relativity, nothing could move faster than light. So how could this remote knowledge appear without some hidden mechanism? The EPR paper argued that either quantum mechanics was incomplete, missing, hidden, variables that prearranged the answers, or else the world was somehow non-local, allowing a kind of invisible thread between distant points. The challenge rippled quickly across the scientific world. In Copenhagen, Niels Bohr, who had become the quiet general of quantum interpretation, took the paper as a direct attack. Bohr's laboratory at the Carlsberg estate had been a haven for young physicists since the 1920s, a place of coffee-fueled arguments and chalkboards layered in equations. He read the EPR paper carefully, line by line, and began to draft his reply. Yet Bohr's answer, published later that same year, did not soothe the debate. It deepened it. He insisted that Einstein's reasoning misread what physical reality meant in quantum theory, that the very act of measurement changed the thing being measured, and that the sharp categories of classical physics could not survive at this scale. His words were precise, but too many impenetrable, dense paragraphs filled with terms like phenomenon and complementarity, the philosophical armor he had worn since the famous Solvay conferences where he and Einstein had sparred face to face. Einstein, for his part, was unsatisfied. He felt Bohr had evaded the core issue. He wanted a world where objects had definite properties whether or not we looked at them, and Bohr seemed content with a world that was slippery until pinned down by an observation. Friends who witnessed their exchanges, like Leon Rosenfeld and Wolfgang Pauli, described them as battles of temperament as well as intellect. Einstein, calm and geometric. Bohr, intense and elliptical, circling ideas rather than striking them. At the 1930 Solvay meeting in Brussels, years before EPR, Einstein had rolled out one clever thought experiment after another, boxes of light, slits, and clocks. Only 4 Bohr to parry each one overnight, often appearing the next morning with a new diagram and a deeper argument. By 1935, the duel had moved from conference halls to printed pages. But the stakes felt the same. The paradox they left behind, now called the EPR paradox, still shadows physics. Decades later, John Bell would translate its philosophical tension into a set of hard inequalities, and Alan Aspect's experiments in the 1980s would show the quantum world violating those inequalities, leaning toward the very non-locality Einstein disliked. Yet even as data piles up, the meaning of that non-locality, what exactly is real? What exactly is communicated, if anything remains unsettled? Some say the particles share a single wave function that never really splits. Others that reality itself has no definite state until it is touched by measurement. And a few search still for hidden gears. Beneath the quantum fog, what makes this episode so enduring is not only its technical bite, but its human shape. Einstein, weary of probability and eager for clarity, Bohr, protective of the fragile but triumphant new theory. Young Podolsky and Rosen lending formal rigor to their elders' intuition. The settings themselves carry a mood. Princeton's Institute for Advanced Study, quiet hallways lined with blackboards. Copenhagen's city streets wet with spring rain as Bohr walks and mutters to himself. European trains carrying letters and preprints back and forth. The world in 1935 was edging toward war and fracture. Yet in these rooms, the battle was over reality's code. And after nearly a century, the question they framed has not been erased. Ask a physicist today whether quantum mechanics describes the whole truth or only the surface, and the conversation will often drift back to that paper, its cautious opening lines and its final provocation. We have built technologies from quantum rules, lasers, chips, secure communication, but the intellectual expedition Einstein, Podolsky, and Rosen began remains unfinished. They set out to chart the hidden landscape behind appearances and found instead a deeper mystery. One that still makes us wonder what is real and what is simply written into the silent order of the universe. In April of 2019, a small group of scientists gathered in rooms scattered across the globe to watch an image appear on their computer screens. An image that had taken 2 years of processing. A planet's worth of radio dishes and more patience than most people can imagine. On the monitors came a dark circle framed by a thin ring of fire. It's not literal flames, but light bent and twisted by gravity until it wrapped back on itself. This was the first photograph of a black hole. The supermassive one at the heart of the galaxy M87, 55 million light-years away. And it seemed to prove that even the wildest predictions of physics had taken root in reality. To see it was to feel time stretch, an echo of Einstein's equations from 1915, of Karl Schwarzschild's letter from the Russian front describing a solution to those equations that no one then believed could exist, and of decades spent turning theory into vision. Black holes had long been the most secretive objects we could imagine. They are born when massive stars die and collapse inward, squeezing all their matter and history into a point so dense that not even light can escape. Around them lies the event horizon, that silent boundary where escape velocity equals the speed of light. Anything that crosses gas, dust, entire worlds is believed to be gone from our view forever. For many years, physicists thought black holes were perfect cosmic shredders, swallowing whatever dared to fall in and hiding it beyond any hope of retrieval. The idea was dramatic and clean, but it also clashed with one of quantum theory's quiet but unshakable rules. That information about a physical system can never be truly lost. In the 1970s, a young British physicist named Stephen Hawking set out to study the edges of black holes more carefully and made a discovery that startled everyone, including himself. Using quantum field theory in the curved spacetime around a black hole, he found that black holes are not completely black. They glow faintly. The effect is tiny, but real. Pairs of particles form just outside the horizon. One falls in while the other escapes, and in this way, the black hole slowly leaks energy and shrinks. Today we call it Hawking radiation. Over immense spans of time, longer than the current age of the universe, a black hole could evaporate completely. That alone was stunning, but the deeper question was worse. If a black hole evaporates away, where does the information about what fell in go? Quantum mechanics says the total information must remain. Hawking's early calculations seem to say it vanishes. This information paradox, as it came to be known, sparked a furious debate that lasted decades. On one side stood Hawking, insisting that black holes destroy information, that nature is not obliged to keep every detail. On the other side stood a growing band of physicists who felt the quantum rule could not be broken so easily. Among the most vocal was Leonard Susskind, a young theorist then at Stanford, who along with Gerard T. Hooft and others fought to preserve the principle of information conservation. In the 1980s and 1990s, Susskind helped build what became known as black hole complementarity, the idea that information is not lost but scrambled beyond recognition and later released in the radiation itself. Another step came from the holographic principle, a radical suggestion that the contents of any region of space might be fully described by information on its boundary, like a 3D scene encoded on a 2D surface. If that were true, then a black hole's event horizon might be less a one-way curtain and more a densely woven record of everything that falls through. The fight between Hawking and Susskind was not polite. It stretched across conferences and papers, full of bets and public challenges, yet it was also oddly inspiring a deep human argument about whether the universe keeps faith with its own laws. Over time, evidence and new calculations began to favor the information keepers. In 2004, after years of defending his position, Hawking conceded in a public talk at the Dublin Conference on General Relativity, admitting he had been wrong and that information does survive, though in a form so scrambled it is effectively unreachable. He later paid off a famous wager with John Presgill, handing him a baseball encyclopedia to symbolize the returned information, the photograph of M87's black hole. Though not a direct test of the paradox, arrived as a kind of visual punctuation to this long intellectual battle. The Event Horizon Telescope, an array of 8 radio observatories, stretched from Hawaii to Spain to the South Pole, had spent April 2017 capturing radio waves with astonishing precision, then combined them into an Earth-sized virtual lens. The data were immense and fragile. It's flown on hard drives from observatory to supercomputer because the internet could not carry so much. When the final picture appeared, it showed the very rim where Hawking radiation would whisper, where Susskind's holographic ledger might hold its records, that glowing orange ring is light bent almost back on itself by gravity. The shadow is the place where light cannot return, but where, if theory is right, information still clings in some subtle, almost metaphysical way. To look at that image is to stand at the edge of knowledge and also of memory. Here is a place where nothing escapes, and yet the universe itself refuses to forget. The story of a falling star, the detail of an atom, the pattern of a planet once taken. They may be hidden beyond reach, but not erased. Our tools are still too young to read the script, but the script is there. That is what Susskind and his allies meant when they said information is never lost. It is the cosmos keeping its own diary. Locked behind horizons we can only sketch, in the dark shape at the center of M87. Millions of suns worth of mass-pressed light into silence, but not into nothing. The photograph that never fades is not just the one captured by the Event Horizon Telescope. It is the deeper photograph the universe takes of itself, frame by frame, through every interaction and every particle's quiet bookkeeping. Even where no light can travel back to us, reality remembers. And that quiet promise that nothing is fully gone reaches far beyond black holes, into the heart of why we wonder if thought itself might have a place in the permanent record of spacetime, long before there were stars to burn or planets to wander. Before there was iron in mountains or oxygen in seas, there was a sudden and incomprehensible flash, a birth so dense and hot that for a time no particle could travel freely. No light could find a straight path. The early universe, newly born some 13.8 billion years ago, was a blinding soup of energy and matter, so crowded and turbulent that photons, the carriers of light, were trapped in an endless dance with electrons and protons, scattering and colliding in every direction. For hundreds of thousands of years there was no clear view, no open sky, only the restless fog of a cosmos still making itself. And yet, hidden in that chaos was the seed of something that would one day let us look back further than any eye or telescope. could dream a faint whisper of radiation, stretched thin but not lost, waiting like an old photograph in an attic no one had entered yet. Around 380,000 years after the Big Bang, a moment often called recombination, the universe cooled just enough for electrons to settle into orbits around protons, forming the first stable hydrogen atoms. The fog lifted almost at once. For the first time, light could travel without being trapped and reabsorbed. Photons, once imprisoned, streamed outward in every direction, carrying with them a perfect imprint of that early time, the density of the infant cosmos, its tiny ripples, its first breath of structure. Those photons did not stop. They traveled for eons, stretched by the expansion of space itself until their energy fell into the microwave part of the spectrum. They still travel now, filling every corner of the sky. So faint, they seem like silence until you build a receiver sensitive enough to hear them. We call this ancient glow the cosmic microwave background, or CMB. And to look at it is to look at the oldest visible memory the universe keeps. For a long while, no one expected we could ever see such a thing. It was theory whispered into equations. In 1948, Ralph Elfer and Robert Herman, following ideas from George Gamow, predicted that if the universe had begun in a hot, dense state, there should be leftover radiation cooled by expansion, but still detectable as a uniform microwave hiss. Their estimate was close, about 5 degrees above absolute zero. Yet the idea drifted on the margins of cosmology until, by chance, it was discovered. In 1964, Arno Penzias and Robert Wilson, radio engineers working at Bell Labs in Holmdel, New Jersey, tried to track down an annoying background noise in a great horn-shaped antenna originally built for satellite communication. They cleaned away pigeon droppings, checked the electronics, turned the dish in every direction, and still the faint static remained. Across the river at Princeton University, Robert Dick and his team were preparing to search for just such a signal. When Penzias and Wilson called to compare notes, the pieces fit. The hiss was the afterglow of creation itself, echoing from a time before galaxies. That accidental discovery changed cosmology forever. But the photograph itself was still crude, like a child's first sketch. It showed that the CMB was real and nearly uniform, but details the tiny temperature fluctuations that would later grow into stars, clusters. And the filaments of cosmic web were beyond the sensitivity of the Bell Labs instrument. In the late 1980s and early 1990s, NASA launched the Cosmic Background Explorer, or COBE, under the leadership of John Mather and George Smoot. COBE's measurements, released in 1992, mapped the microwave sky with unprecedented care, revealing minute variations, parts in 100,000, across the heavens. These small differences in temperature were not noise, but the first seeds of cosmic structure, the ancestral imprint of everything we know. George Smoot famously said it was like looking at the face of God, though what he meant was the face of the universe when it was only a baby. Years later came WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, and then Europe's Planck satellite in 2009. Each improved the clarity of this ancient photograph, sharpening our view of the first light. Planck's Full Sky Map, released in 2013, offered the most precise picture of the early cosmos ever made, a mottled pattern of red and blue. Spots that are not stars or galaxies, but the very first unevenness in the primordial plasma. From those faint differences grew everything: the Milky Way, the Andromeda Galaxy, the planet under our feet, and the bodies we inhabit. The picture is both strangely modest and almost unbearable in its significance. A pattern of warmth and coolness just after time became transparent, carried to us on waves that have been traveling since before there were even stars to burn. To hold an image of the cosmic microwave background is to hold proof that the universe remembers where it came from. Light that left when there was no Earth, no sun, no heavy elements. It has crossed billions of light years and still carries a map of the first moment when seeing became possible. When we build detectors cold enough and precise enough to catch that radiation horn antennas, bolometers chilled near absolute zero, we are listening to the faint hum of our own beginning. The data arrive as numbers, but in them is poetry. The universe took a photograph of itself as an infant and never let go. There is something deeply human in the way we reach for this memory. People have always kept records, carvings on bone, paintings on cave walls, photographs tucked into books. The cosmic microwave background is the universe doing the same, without needing hands or eyes. It is a record written not in ink, but in radiation. A message that says, I was once young, hot, and full of possibility. We can read it now. From small rooms on Earth with satellites orbiting quietly overhead is a miracle of patience and curiosity. Even the noise on an untuned television set once contained a faint echo of this light, a scattering of those ancient photons striking the antenna and turning into a hiss and a shimmer. Every household with an old cathode ray screen once saw, without knowing, the birth cry of the cosmos. Today our instruments are far more refined, but the wonder remains the same. Against the vast silence, the memory of light still whispers, telling us that beginnings are not erased, that the first story the universe told is still traveling outward, and can still be found by anyone willing to listen, in the far southern reaches of our planet, where the sun can linger above the horizon for months and then vanish for just as long. Human beings have learned to treat the ice itself as a book. It is not a book with paper or ink, yet each layer is a page, written in snow that fell year after year, pressed into fern and then into deep blue ice by the weight of centuries. When scientists set out across the Antarctic plateau or the high interior of Greenland, they do not search for treasure in the usual sense. They search for columns of frozen time, long cylinders drawn from beneath. They're boots that contain air older than any kingdom, and dust from skies untouched by modern engines. It is work both delicate and brutal, because the cold and the distance can break machines and people alike, and yet the reward is a direct conversation with a past no living witness can recall. The first serious attempts to read these frozen archives began in the middle of the 20th century. As glaciology matured from a rough fieldcraft into a careful science, in Greenland, the Camp Century project of the early 1960s cut a hidden base into the ice. Ostensibly a U.S. Army experiment, but also an ambitious scientific platform. Their Danish and American teams drilled deep, and in 1966 reached more than 1,300 meters down, pulling up ice that had formed over 100,000 years before. Each meter was a page, and within those pages were tiny bubbles, actual pockets of ancient air, sealed since before the last ice age ended. A few years later, similar efforts on the Antarctic side began at places like Bird Station and Vostok, remote and almost lunar in their isolation, where temperatures could drop below -80 degrees Celsius, and yet drilling rigs kept turning. To handle an ice core is to hold the breath of vanished worlds. Each winter's snow traps whatever the sky carried: volcanic ash, soot from distant fires, even radioactive isotopes from events like nuclear tests or supernova remnants that sprinkled the upper atmosphere. More important still is the simple air itself, frozen in place and faithful to its composition. When technicians in white coats slice a core in cold laboratories in Copenhagen or Colorado and draw gas from a bubble the size of a pinhead, they can measure the carbon dioxide, methane, and oxygen ratios from a time when mammoths walked and humans were scattered bands of foragers. The famous Vostok core, drilled by Soviet and later Russian and French scientists through the 1980s and 1990s, reached back for 120,000 years and revealed with quiet authority the rhythmic rise and fall of greenhouse gases tied to ice ages and interglacial warmings. Later, the EPICA European project for ice coring in Antarctica core pushed even further. Beyond 800,000 years, letting us see 8 full cycles of climate breath, there is poetry in the details. A thin layer of acid in one section can mark the eruption of Mount Tambora in 1815, whose ash darkened skies and chilled global harvests. A band richer in sulfate tells of the even older blast of Thera in the Bronze Age, a faint but measurable spike of carbon-14, shows when cosmic rays flared from a nearby stellar event, perhaps the one that struck Earth around a D 774, recorded in medieval chronicles as Strange lights in the sky. Even human folly is caught. The mid-20th century. Spike in radioactive isotopes from above-ground nuclear tests sits there like an undeniable footnote. The work of retrieving these time scrolls is as physical as it is intellectual. Crews live in tents that crackle in the polar wind, their generators drumming steadily while outside temperatures plummet to levels where steel groans. Drillers use long hollow bits to cut deep into ice that is hard as rock, then hoist up sections 3 meters at a time, brushing off frost and sealing them in plastic sleeves. These cores are flown out carefully, wrapped and chilled, to labs thousands of kilometers away. Each one is handled with reverence, because it is not just ice. It is a record no library could hold, in Greenland's Nem camp in 2010. Researchers celebrated when they reached ice from the Eemian interglacial, about 128,000 years ago, a time when the world was warmer and seas higher than today. They could read in the trapped air how carbon dioxide and methane levels behaved, how abrupt climate shifts unfolded. In Antarctica, at Dome Fuji and Dome C, teams have sat through endless winters, months of darkness broken only by generator lights and radio contact with the outside world, to push the record deeper still. Their findings shape not only climate science, but our sense of permanence. It is one thing to talk about ancient change. It is another to hold it in your hands. This ability to summon the deep past from silent matter feels close to the idea of a universe that never forgets. Here, memory is not in neurons or diaries, but in the quiet fidelity of nature. Snow fell, one winter after another, capturing the sky's breath and then sealing it beneath newer snows, until time itself pressed it into clarity. When we draw it up, we are, in a sense, asking the planet what it remembers. And the planet answers with numbers and ratios, yes. But also with the unspoken truth that nothing simply vanishes. The ice teaches humility. The air we breathe today will settle eventually into future layers, carrying the signature of our engines, our cities, our fires. Some unknown scientists, thousands or tens of thousands of years from now, might drill into those layers and measure our present as carefully as we measure Rome's volcanoes or the Mammoth Steppe. In that sense, we are not just living, we are writing whether we wish to or not. There is something haunting in knowing that memory is everywhere, waiting in glaciers, locked in stone, drifting as faint light across the cosmos. The ice cores of Antarctica and Greenland remind us that the universe does not rely on our recollections. It keeps its own notes, quiet but indelible. In a place where nothing grows and almost nothing moves, time itself has become visible, a frozen library more honest than any human record. To tap it is to glimpse the deep patience of Earth, and to realize that forgetting, at least on a cosmic scale, may be far rarer than we think, far below the surface of the Earth. In caverns that once echoed with the noise of drills and the slow groan of stone, a new kind of listening has taken shape. These are not mines in the old sense, no longer hungry for ore or coal. They have been remade into instruments. Their dark tunnels and vast chambers turned toward the sky, not with glass or steel, but with silence and water. Here, in places like the Super Cameo Kondi detector in Japan's Mozumi mine or the Sudbury Neutrino Observatory in Ontario's Creighton mine, scientists gather signals that pass through nearly everything without a trace. Messengers so elusive that billions fly through your body each second unnoticed. These messengers are neutrinos, born in the heart of stars and in the cataclysms of supernova, and by catching even a few, researchers have found a way to read events older and farther than light can sometimes tell. The Super Cameo Kondi experiment, it's often called Super K, lies 1,000 meters underground in the Japanese Alps near the town of Hida. It was built in a chamber big enough to fit a 12-story building, lined with smooth concrete and filled with 50,000 tons of ultra-pure water, so clear it seems invisible. Around the water tank are more than 11,000 golden photomultiplier tubes, each as round as a beach ball, designed to catch the faint blue flashes of Cherenkov radiation, light made when a neutrino slams into a water molecule and produces an electron moving faster than light can travel through water. Though the neutrino itself escapes almost untouched, the tiny aftermath of its arrival is enough to prove it was there. Scientists stand on narrow catwalks above the pool, watching not with eyes but with electronics that can sense single photons of light. It is a cathedral to patience, built not to watch the stars but to let the stars reach in and touch us, a continent away. In Sudbury, Ontario, another deep mine that once yielded nickel has been turned to a different kind of wealth. The Sudbury Neutrino Observatory, or SNO, was hollowed 2 kilometers down, in one of the safest and quietest places humans could make. Because cosmic rays and natural radiation from the surface would drown the faint neutrino signals, if they were not blocked by all that stone. Inside the chamber, scientists suspended a sphere filled with 1,000 tons of heavy water whose hydrogen atoms carry an extra neutron. It sat like a pale planet surrounded by thousands of sensors. And for years it recorded interactions that changed our understanding of the sun itself. In the early 2000s, SNO confirmed that neutrinos change flavors as they travel, solving the long-standing solar neutrino. It's a problem that had puzzled physics since the 1960s. The sun was making all the neutrinos theory predicted. We had simply been blind to their shape-shifting journey. What these experiments share, beyond their daring engineering, is a sense that the Earth's crust can be used as a shield and a lens at once. By going deep, scientists create a silence where the rarest whispers can be heard. Neutrinos are nearly massless and interact so weakly that light-years of lead would barely slow them. They come from nuclear reactions in the sun, from collapsing stars so distant their light is only a faint smear now, and from cosmic events so violent they would tear any matter we know to pieces. In 1987, when a star exploded in the Large Magellanic Cloud, a supernova, 168,000 light-years away, a handful of neutrinos arrived at detectors on Earth, hours before the star's light grew bright enough to see. At Kamiokande 2 in Japan, and the IMB detector in the United States, just a couple dozen faint flashes told astronomers that something titanic had happened long before telescopes could confirm it. It was the first time humans had been alerted to a cosmic death, not by light, but by these ghostly particles. This is why some call these mines time machines. They do not let us travel, but they let the past reach us in ways light cannot. Because neutrinos slip through matter with almost no resistance, they carry unspoiled information from places light would have scattered or been delayed. In the heart of the sun, where photons may bounce for thousands of years before escaping, neutrinos fly out in seconds. The ones hitting those tanks tonight left the core of our star 8 minutes ago and tell us how fusion is unfolding right now. Those from distant supernova tell us about the birth of heavy elements, iron, gold, uranium, the very materials our bodies and our machines depend on. By reading them, scientists look deeper into time than any photograph could reach. The physical labor behind these elegant measurements is enormous. To make Super K, crews lowered thousands of delicate detectors one by one, each tested and sealed against leaks. The water must be kept pure to a level beyond drinking water or even hospital standards, constantly circulated and filtered so nothing dims the Cherenkov glow. In Sudbury, miners and scientists worked side by side to build the acrylic sphere and fill it. With heavy water borrowed and carefully returned after the experiment ended, its value was so high it was guarded as closely as any vault. Even today, new detectors like IceCube at the South Pole push further, embedding sensors deep in clear Antarctic ice to catch neutrinos from across the universe. To stand in one of these caverns is to feel small in a way that is not frightening, but reverent. A kilometer of rock above you, instruments around you waiting to hear events that began long before the first cities, and above that, the endless sky. We have turned abandoned mines, symbols of human hunger and industry, into observatories of pure wonder. They remind us that the universe does not shout. Most of its deepest truths arrive as faint tremors and single flashes of light in dark water. Every neutrino caught is a memory delivered. It might be the echo of a star that lived and died before Earth had mammals, or the pulse of our own sun's steady fire, or the remnant of a cosmic ray born beyond the Milky Way. by building places quiet enough and patient enough. We make it possible for the past to speak. In this way, our planet itself becomes a listening device, turning minds once dug for metal into chambers where the universe can send its oldest secrets and be heard. If you hold a warm cup of tea in your hands on a cold morning and feel it cool slowly against the air, you are watching one of the deepest rules of the universe at work. That simple drifting of heat from cup to room, from fingers to breath, is part of what physicists call entropy. A word that can sound forbidding but really points to something both humble and profound. It means that energy, once concentrated, tends to spread out. That ordered states shift toward disorder. That time seems to have a direction because of this quiet spilling. Yet hidden in that same law is another truth that people rarely notice as things spread and mix. They do not erase the fact of what happened. They only hide it in finer detail. Each event leaves a trace, however faint. And those traces accumulate like a secret diary written by the universe itself. This insight took centuries to surface. In the 19th century, steam engines and the Industrial Revolution pushed scientists to think hard about heat and work. One of them, Ludwig Boltzmann, an Austrian working in the 1870s and 1880s, had the audacity to imagine that heat was nothing but countless invisible particles in restless motion, colliding and sharing energy in ways too fast for the eye, but clear to mathematics. From this picture he derived a formula so elegant it was later carved on his tombstone in Vienna's Zentralfriedhof. S equals K log W. In a few symbols, it says that entropy S measures how many ways W the tiny parts of a system can be arranged while still looking the same overall. The K is just a constant with his name attached. But the idea behind those letters is huge. The more ways something can happen inside without changing how it looks outside, the higher its entropy. Imagine a child's room after a day of play. At first, the blocks are stacked neatly, only one or two possible arrangements. As the day goes on and blocks scatter, the number of possible messy states explodes, and so does the entropy. Yet if you were impossibly patient, you could, by looking at every mark and angle, know where things came from, because the scattering itself is a record of the earlier order. Boltzmann understood this and saw that disorder is not nothingness. It is the vast catalog of all paths a system could take from where it was to where it is now. For him, this was more than academic. Boltzmann wrestled with the meaning of time's arrow, why we feel past and future so differently. His statistical vision said that the past is the rare, low-entropy arrangement we remember, and the future is the almost endless spread of higher-entropy states. Yet memory, in some quiet way, grows with that spread, not against it. When the tea cools, molecules bump and exchange energy. And though you can no longer reverse it, the state of the room now encodes what happened. To forget in human terms to lose the sensation of warmth is not the same as erasure in nature. The ledger still updates every collision another entry. Standing at Boltzmann's grave, one can see the contradiction that weighed on him. His simple formula explains so much. But it also reveals how delicate low-entropy order is and how unstoppable its decay. Some historians think his struggle with these ideas, along with personal hardship, contributed to his despair before his death in 1906, yet the power of his work has only grown. Today, every field, from cosmology to information, theory leans on the idea that entropy is not just about heat, but about knowledge, or rather, the cost of losing it. Physicists like Claude Shannon later borrowed Boltzmann's statistical approach to define information itself. The similarity is not coincidence. Entropy and information are siblings. To say something has high entropy is to say there are many possible microstories behind the same outward face. So it would take more bits of information to describe it exactly. When you shuffle a deck of cards, you raise its entropy because there are so many possible orders. Yet the cards themselves quietly hold the proof of the shuffle. If you could examine every molecule, every slight bend and scratch, you could in theory reconstruct the path they took. It is unimaginably complex, but not gone. This is where the paradox enters. Forgetting still writes. When a photograph fades in sunlight, the bleaching molecules record the event by their very change. The lost picture has become a new pattern that carries its own story. When a house burns, the ash and smoke encode what once stood there in the arrangement of carbon and the spread of soot through air currents. On a cosmic scale, stars die, and their debris swirls into new worlds. But the debris itself is testimony. Even black holes, once thought to obliterate all memory, are now believed to keep information at their horizons and slowly return it through Hawking radiation. The universe seems constitutionally opposed to true deletion. You can feel this law quietly shaping your own life. Every word you speak changes the air. Every step rearranges grains of sand or dust that will, in principle, never return to the same order. Entropy grows, but so does the permanent record of having been. That record may be too fine for any brain or machine to gather, yet it exists. This is the ledger physicists speak of, not a book with neat lines, but the sum of physical states, each one carrying forward the consequences of the last, and because entropy drives time forward. This ledger also gives us direction. It is why we remember the past, but not the future. We swim in a rising sea of microhistories that have already been written, while the future is still unrecorded. Boltzmann's grave marker, simple black stone with gold letters spelling S equals K log W, is a quiet monument to this idea. Tourists in Vienna pause there and take photographs, adding their own layer of irreversible change to the moment. Their cameras scattering heat and light, their footsteps rearranging dust, all tiny, permanent updates to the world's account book. So when you hold that cooling tea, or watch autumn leaves crumble underfoot, you are witnessing a universal accounting process. The warmth you lose, the crispness fading from each leaf, is not vanishing into nothing. It is becoming part of the deep, unstoppable story of the universe. Entropy ensures change and makes forgetting possible, but it also refuses to let any event vanish without consequence. In this way, the cosmos remembers more than we ever could, even in its growing disorder, across the wide and silent deserts of the earth, where the air is thin and the ground holds heat long after the sun has slipped behind the horizon. There are places where the land itself has kept records no librarian could organize and no historian could fully translate. These are not gentle diaries, but archives written by violence and sudden change, a meteor's fire, an atomic blast, a lightning strike of cosmic dust, all sealed into glassy stone and mineral scars. The deserts, stripped of rain and cloaked in dryness for thousands or even millions of years, become natural vaults where such records survive. Pages that cannot rot because nothing grows thick enough to erase them. If you know how to look, you can walk into these empty spaces and read stories of worlds ending and beginning again, written in a script of fused sand and shattered crust. One of the most haunting of these chapters lies in the Libyan desert of the Sahara. Scattered across a broad swath of pale sand is a strange, almost luminous yellow-green stone known as Libyan desert glass. Some pieces weigh less than a pebble. Others are the size of a fist. They were first noted by travelers and nomads centuries ago, and puzzled over by geologists in the early 20th century. But their true origin remained a mystery until late in the last century. Analysis showed that the glass is almost pure silica, created by heat far beyond what volcanoes or wildfires can achieve. The leading explanation is that, perhaps 29 million years ago, a meteor or comet exploded with unimaginable force above the desert, its shockwave melting sand into liquid, and then cooling it so fast that glass formed. The pharaoh Tutankhamun's burial pectoral, found in his tomb in 1922, includes a carved scarab of this very glass, a jewel older than the Nile, born from a sky that tore itself apart. Elsewhere, in the barren reaches of Chile's Atacama Desert, scientists read an archive of the heavens that comes not just from ancient impacts, but from the slow fall of cosmic dust. The Atacama is one of the driest places on Earth. Some weather stations there have never recorded rain. That dryness and stillness mean that for hundreds of thousands of years, microscopic spherules from meteor trails and distant stars have settled and stayed, barely disturbed. When teams sift its soil, they find tiny metallic beads, droplets of iron and nickel that once burned white-hot as they pass through the atmosphere. They also find layers rich in nitrates and rare isotopes. Traces of supernova events that showered Earth long before humans thought of charting the skies. Because the Atacama hardly changes, these layers remain legible, a cosmic guestbook. Each grain of sand keeping secrets of past cataclysms. Yet not all of the desert's records are cosmic. Some come from us. On July 16, 1945, at a remote stretch of Jornada del Muerto Valley in New Mexico, the first nuclear device was detonated. The blast, codenamed Trinity, vaporized the steel tower that held it and fused the desert floor into a strange green glass, later called trinitite. When the scientists returned to the site after the mushroom cloud had cleared, they found sheets of this glass shimmering like sea foam under the harsh sun. Trinitite is accidental geology, an artifact born in seconds, but now as permanent as any volcanic rock. It holds within it traces of the bomb's design, isotopes of barium, lanthanum, plutonium's ghost, sealed into the silicate structure. Though the site was bulldozed and fenced, pieces still exist, collected and studied. Each fragment a footnote of how human technology once outshone the sun for a fraction of a second. The idea that we leave permanent scars is not confined to Trinity. Across the Nevada test site, across Semipalatinsk in Kazakhstan, across islands in the Pacific, the Earth's crust has been tattooed by nuclear detonations, each one carving a signature of glass-lined craters and altered minerals. These changes will outlast memory, outlast cities, and perhaps even outlast the species that made them. Future geologists, or whoever digs here long after we are gone, will read our ambitions and our fears in the glass we forged. Even older than nuclear fire are the tektites small. Dark glass droplets scattered across regions of Asia and Australia, products of impacts millions of years past. The Australasian strewn field, created about 790,000 years ago, by an impact somewhere still debated, covers a tenth of the globe with these silent witnesses. Each one is a cooled tear of molten earth hurled into the sky and rained back down. They have no inscription, but their shape and chemistry are unmistakable. Proof of an event so intense it changed. Landscapes and skies in an instant. Deserts keep these messages because they erase so little. Rain and plants and ice, the great editors of the planet, are absent or weak there. What happens in the Sahara or the Atacama can linger as if time itself had slowed. In some places, the footprints of Apollo training missions still mark Nevada dust decades later. In others, World War II practice bombs have left scars beside petroglyphs carved thousands of years before. Geology becomes a palimpsest, but one where nothing is fully lost. To stand in such a place, say on the edge of the Trinity, site where the ground still glimmers faint green, or among the quiet dunes where Libyan glass catches the light like broken bottles, is to feel how events refuse to disappear. Even a single second of heat or force can leave a note that endures for millions of dawns. The Earth, indifferent and patient, keeps the memory when we do not. This endurance binds human story to cosmic story. We think of deserts as empty, yet they are full of time. A wandering traveler in the Atacama might brush away sand and touch a meteor bead older than mammals. A future scientist may dig where we once tested bombs and know, without reading a book, the shape of our first nuclear age. The land's archive is quiet but complete. It does not care why something burned or fell or exploded. It only records the fact and holds it steady against the wind. Such knowledge changes how one thinks about legacy. Even without intention, we inscribe ourselves into the crust and dust. Some of those marks are wonders, glass from the sky turned to jewels, star remnants in desert soil, and some are warnings. The unintended memorials of our fiercest inventions. Together they remind us that forgetting is a luxury of minds, not of matter. The deserts, with their silence and unblinking sun, write everything down and wait for someone to return and read. It is a strange and almost dreamlike notion that the vast interior of reality, with its stars and tides and human memories, might in some deeper way be written not throughout its volume, but on its skin. Yet this is what a growing number of physicists have come to suspect, that the universe may be holographic. That every event which seems to happen in 3 dimensions could, at the most fundamental level, be stored and described on a distant boundary, like patterns of light on the surface of a soap bubble. The word holographic here does not mean illusion, not in the sense of a trick or a mirage. It means that the full richness of what we experience could be encoded elsewhere in a form so dense and complete that, if one could read it, nothing would be missing. It is an idea so audacious that when it was first proposed, it sounded like philosophy disguised as physics. But decades of hard work and quiet argument have slowly made it respectable, perhaps even necessary. The seed of this thought can be traced back to struggles over black holes and information in the 1970s and 1980s, when Stephen Hawking suggested that black holes could evaporate and perhaps destroy information. It threatened to break one of quantum theory's most sacred rules. A Dutch physicist named Gerard T. Hooft, working at Utrecht and later often in dialogue with colleagues at CERN, began to consider whether the information swallowed by a black hole might not be lost, but could somehow be stored on the horizon itself, the 2-dimensional surface that marks the point of no return. Instead of vanishing into an unreachable core, every detail about the matter that fell in could be scrambled and stamped onto that surface. Leonard Susskind at Stanford, already wrestling with the same paradox, seized on this insight and helped turn it into a broader principle. If it works for black holes, why not for the universe as a whole? Maybe everything inside a region of space can be fully represented by bits of information living on its boundary. Susskind and T. Hooft spent the 1990s arguing, writing, revising, and challenging one another in seminars and papers. Their debates were not combative in the way of public quarrels, but they were urgent and deep, circling the same question with different tools. Susskind favored a flexible string theory approach, drawing on the mathematics of vibrating one-dimensional objects and how they might store information. T. Hooft, coming from a more conservative quantum field theory tradition, wanted the idea to rest on clear counting of quantum states and symmetries. Both men found encouragement in a separate and breathtaking result that came from string theory. In 1997, Juan Maldaceni's A DSCFT correspondence, Maldacena showed that a certain kind of universe with gravity could be exactly equivalent to a universe without gravity living on its boundary. A hologram so precise, it felt like a proof of concept. What had been speculation suddenly had a mathematical playground. These breakthroughs gave new shape to the old intuition that boundaries matter more than we thought. In classical physics, the inside of a sphere is the main story. The surface is just where it stops. In holographic thinking, the surface could be the real archive, every fluctuation inside recorded and represented there. The number of possible quantum states in a region appears to scale not with its volume, as you might expect if each cubic centimeter were free to store its own data, but with the area of its surface measured in Planck units, unimaginably tiny squares about. This area law for entropy was first hinted at by Jacob Bekenstein in the 1970s while thinking about black holes. It became a guidepost. The true bookkeeping of reality seems to prefer surfaces. To walk mentally into one of these seminars in the late 1990s would be to hear heated but careful voices. Susskind sketching with chalk at Stanford's Varian Physics building, T. Hooft defending his reasoning in workshops at CERN. Young theorists scribbling notes and wondering if they were witnessing a quiet revolution. The question was not just academic. If the holographic principle is true, it changes how we think about the fabric of space. About whether locality, the idea that things only affect their immediate neighbors, is fundamental or just an approximation. It even hints that our familiar 3-dimensional world might be like a projection from a deeper 2-dimensional code. Yet this strangeness carries a deep reassurance for the theme we have been following: memory. If the universe really is holographic, then nothing that happens inside can truly fall away. The edges hold the record. In a black hole, the event horizon's quantum jiggle keeps track of every particle that crossed. In the cosmos as a whole, some distant, observable boundary, perhaps the farthest edge of space-time we can never reach, may keep the master copy of all events. Even if matter dissolves and light fades, the pattern would persist as a kind of cosmic backup. No one pretends this picture is fully proven. It is a web of insights and partial confirmations, not a closed theory. But each year it becomes harder to dismiss. Calculations of black hole entropy agree with the area law. Quantum gravity, a theory still incomplete, seems to demand some holographic behavior to stay consistent. Even condensed matter physicists, working on exotic materials in laboratories, use holographic ideas to model strongly interacting systems too hard to solve otherwise. The principle has escaped its birthplace and roams widely. A sign it may have touched something true. What is most haunting is how naturally the holographic view merges with the older intuitions about a universe that remembers. We once imagined information locked deep inside matter or hidden in inaccessible corners. Now the suggestion is that reality itself is designed to keep the ledger safe at its edges, as if the perimeter of existence were a great wall of memory. For human minds used to things fading, this can be dizzying, even if the inside burns or collapses. The story has already been copied. When Susskind recounts those early struggles in his books and lectures, there is a mix of humility and quiet awe. What began as a fight to save quantum law from the abyss of black holes has opened a door onto a universe stranger, but perhaps more faithful than we dreamed. It says nothing done is ever truly undone. The edges know. And though we cannot yet read that script, its mere possibility deepens the sense that reality itself is a keeper of all things. That somewhere, just out of reach, the whole play of existence is inscribed and waiting. In July of 1969, when Neil Armstrong's voice crackled across the airwaves in 500 million, people leaned toward their televisions to watch the first human steps on the moon. Very few stopped to consider how fragile the record of that moment might be. We imagine history is safe once it is filmed and broadcast. Yet the story of the Apollo missions reminds us that human archives can vanish more easily than we think. Even as the moon itself, silent and unchanging, keeps perfect account of what we have done there. The tale of the lost Apollo tapes is a cautionary thread running through one of humanity's proudest achievements. An almost absurd proof that, while we can cross space, we sometimes fail to hold on to our own memory. The signals that reached Earth on July 20th, 1969, were delicate and raw. Sent from the lunar module Eagle to tracking stations in Australia and California, and then relayed for television broadcast. Those first moving images of Armstrong stepping onto the surface were captured in a slow scan format designed for deep space transmission, not for home sets. To make them viewable, engineers had to convert them in real time, pointing a camera at a monitor to create a broadcast-friendly feed. The original slow scan tapes higher in detail. The truest record of the event were stored at NASA's Goddard Space Flight Center and at other facilities. For decades they sat in labeled boxes thought safe. But archives drift. In the early 2000s, a group of former NASA engineers and historians began searching for those tapes, only to discover that the boxes were gone. They had been removed sometime in the 1970s or 1980s. Perhaps during storage cleanouts, perhaps reused to save money. Magnetic tape was expensive, and the Apollo program was over. No one then imagined a day when we would want to remaster every frame. The world was stunned to learn that the clearest footage of humanity's first steps on another world had effectively been taped over. What we had were copies of copies, broadcast reels, home recordings, news archives, but not the pristine original. Yet the data, in a sense, was not truly gone. After a long hunt, experts recovered better versions by gathering and restoring every surviving copy, including those from Australia's Parkes and Honeysuckle Creek tracking stations. Through careful digital cleaning and merging, they built an image far closer to what the astronauts actually sent. The quest to reclaim those pictures felt like a rescue operation for memory itself, a proof that once something radiates into the world, traces can be found even if the original reel has vanished. The process echoed a deeper truth from physics. Information is stubborn, reluctant to disappear entirely, though our human tools can be careless with it. Meanwhile, above our heads, the moon quietly kept its own record without effort. Every footprint from Apollo 11, and from the later missions through Apollo 17 in December 1972, still lies pressed into the regolith, the fine gray dust that covers the surface. With no wind and almost no atmosphere, nothing erases them. The patterns of landing pads, rover tracks, and discarded equipment remain where they were left half a century ago. LiDAR scans and images from the Lunar Reconnaissance Orbiter show them in remarkable detail. The descent stage of the Eagle at Tranquility Base, the long meandering tracks of the lunar rovers at Hadley Rill and Taurus Littrow, even the dark shadows of experiments like the retroreflectors that still bounce, laser light back to Earth. Lunar dust is an archivist beyond compare. It has been collecting cosmic stories for billions of years, each tiny glass bead formed by micrometeorite strikes. Each layer of regolith preserving the chemistry of solar wind and distant explosions. Scientists studying lunar samples brought back by the Apollo crews have found records of ancient solar storms and cosmic rays older than any earthly rock. In contrast to our lost magnetic tapes, the moon's surface has no impulse to rewrite or reuse. It is a slow ledger, turning every disturbance into a permanent mark. This contrast between cosmic permanence and human fragility is sobering. We build grand missions, but our archives can vanish in a single warehouse decision. Paper burns, film decays, hard drives fail, and even digital clouds depend on servers that will not last forever. The original tapes of the first moon landing proved as vulnerable as letters tossed in an attic. Meanwhile, the act itself, the pressure of boots on alien ground, the blast marks from the lander's descent engine endures untouched, awaiting only eyes and instruments to read it. The moon tape mystery is therefore more than a story about lost media. It is a parable about how memory lives outside us. The cosmos is a tireless recorder, but it is indifferent to our intentions. We wanted those tapes to keep our history safe, yet we lost them. We had no plan to preserve footprints on the moon, yet there they remain. In the cold and airless silence, time almost stands still, and every grain of dust becomes a file. For scientists and dreamers alike, this realization pushes two ways. On one side is a call for care to treat our own archives with reverence, to avoid believing that what is recorded once is safe forever. On the other side is a kind of quiet comfort. Even if we fail, something larger keeps track. The universe, through its own physics, refuses to fully forget. Our signals have radiated outward since 1969. A faint expanding bubble of radio noise carrying Armstrong's words across light years. Somewhere far in the future, it may brush an alien receiver or a drifting relic and replay the moment long after our copies have decayed, so the moon teaches what the lost. The tapes warn, memory is both fragile and unstoppable. Our reels can vanish. Yet the act of stepping off the ladder is written in more places than we control. In the dust of Tranquility Base, in the stray photons still fleeing Earth, in the hearts of those who watched and retold. When we reach for total recall, we often think of perfect human libraries and backups. But there is a deeper, stranger safety net, one that belongs to physics itself. The moon does not curate, but it does not forget. High above our heads, far beyond the thin film of weather and the quiet paths of airplanes, the universe is sending a ceaseless rain of particles. A drizzle so fine and constant that it moves through mountains and cities and human bodies without pause. These are cosmic rays. Fragments of protons and heavier nuclei flung across space by violent events. Exploding stars. Black hole jets, perhaps collisions between galaxies. When they strike the upper atmosphere, they shatter into cascades of smaller particles, among them muons. Cousins of the electron, but heavier and fleeting. Born high in the sky and rushing downward at nearly the speed of light. Billions of them pass through us every minute, unseen and mostly harmless. Yet packed with a power we have only recently learned to use, the ability to see through what seems solid, to map the unknown without touching it. This idea, called moon tomography, grew slowly out of curiosity and ingenuity. In the 1950s and 1960s, physicists studying cosmic rays noticed that muons, though unstable, could survive long enough to reach the ground because their rapid speed and relativity stretched their brief lifetime. They could pierce hundreds of meters of rock before decaying. That persistence suggested a new kind of vision, a way to use nature's own rays as an X-ray machine for the planet itself. If you place sensitive detectors beneath a structure, you can measure how many muons come through. Dense material blocks or scatters them. Empty or lighter spaces let more pass. Over time, the pattern of Mooney counts becomes a ghostly photograph of the object above. One of the first famous tests of this came in Egypt. In the late 1960s, Luis Alvarez, a Nobel Prize-winning physicist known for his work on particle accelerators and radar, turned his attention to the Great Pyramid of Khafre at Giza. He and his team set up moon detectors in a chamber near the base. Aiming to check for hidden rooms or passages without drilling or risking damage, over 2 years, the detectors collected cosmic whispers. Each muon, a message from the sky that had just passed through ancient stone. In 1969, Alvarez announced that the pyramid's interior above their instruments seemed solid, with no large undiscovered voids where they looked. The experiment was a quiet triumph. The universe itself had served as surveyor, its own particles probing monuments far older than our technology. Decades later, the method returned in an even more striking way. In 2017, a project called Scam Pyramids placed advanced muon detectors in and around the Great Pyramid of Khufu, the largest at Giza and older still than Khafre's. These detectors, built with modern nuclear emulsion and gas-filled tracking chambers, recorded muons with far greater precision. The result was astonishing. Evidence of a massive hidden void, at least 30 meters long above the Grand Gallery. The discovery did not show what the space was or why it was built, but it revealed that secrets once thought locked in limestone for 4,500 years had a faint shadow. The particles had passed through and told on the stone. The same principle is at work deep in geophysics. Volcanoes that rise above crowded towns can be too dangerous or too dense to probe with drills or seismic waves alone. In Japan, scientists have used Moin tomography to study the fiery heart of Mount Asama and Mount Iwadake, mapping magma chambers and vents that would otherwise be invisible. On Italy's Mount Vesuvius, where millions live in its potential blast zone, muon images help refine eruption models. Detectors buried in tunnels or placed in boreholes quietly count the rain of particles day after day, building maps that may one day save lives. Even nuclear engineers have begun to adapt the technique, using muons to look inside damaged reactor cores at Fukushima. Without sending humans into lethal radiation, what makes this so haunting is the passive patience of it all. We are not shining beams or drilling holes. We are listening to what has always been falling from the sky. Every mountain, every fortress, every chamber has been soaked in cosmic rays since its birth. And inside those showers is enough information to reveal density and shape. Secrets, it turns out, cannot fully hide. They cast a statistical shadow in the rain of mu. To appreciate the power of this, imagine standing under the weight of a volcano or inside a pyramid sealed for thousands of years. Nothing about the stone suggests it can be read. Yet above you, the atmosphere is alive with collisions, particles splitting and racing downward. A tiny fraction of those muons strike a sensor, leaving a trace of their arrival, and slowly, with patience measured in months or years, a picture forms. Dense basalt shows as darker regions where fewer muons get through. Hidden caverns light up as pale leaks where the count jumps. In a control room far away, scientists watch as data points gather into shape, like a Polaroid developing in silence. This way of seeing also hints at a deeper truth about the universe's memory. If even the most hidden spaces leak their presence through cosmic rain, perhaps nothing in reality is fully sealed. The same logic that lets us find a void in a pyramid or the pathway of magma might, at some fundamental level, mean that all events leave signatures not easily erased. The cosmos is not just recording our actions in starlight and gravity, it is bathing us in an endless shower of witnesses. Muon tomography is still young compared to ancient crafts of mapping and digging, but it has already redrawn how we approach the unknown. It is non-invasive, almost reverent, and yet astonishingly effective. Where explorers once chipped and drilled, now they wait and count. Where archaeologists feared to harm relics, they can let the sky do the work. And where geologists once guessed at underground fire, they can sketch its chambers in fine detail. Perhaps the most remarkable part of all is the way it ties the distant universe to our immediate ground. Particles born in events so far away, we cannot name them. Perhaps supernova millions of light years distant are helping us navigate our own world. They arrive after journeys longer than history and end by telling us about chambers and tunnels and molten rock under our feet. It is a quiet reminder that the boundary between cosmic and human is thinner than we think. Secrets may seem safe under stone or ash, but in a universe filled with messengers, even the deepest darkness leaves a faint but faithful outline. In the tense years after the Second World War, when borders hardened and mistrust deepened into the long shadow we now call the Cold War, a quiet revolution was taking place high above the planet. While diplomats argued in public and armies paraded on television, engineers and scientists hidden inside. Anonymous hangars and windowless offices were building machines that would change how the Earth could be known. Their goal was not beauty or discovery, it was survival and advantage. Yet in chasing those goals, they created something extraordinary and lasting, a photographic memory of the planet itself. Frame after frame, continent by continent. So complete that even today we are still uncovering what it remembers. The United States. Fearful of surprise attacks and desperate to understand the true scope of Soviet power, launched the first of these machines in secret in 1960, the project carried a dull, misleading name, Corona. Its satellites were built to orbit high and silent, snapping photographs with film that no one would see until the canisters fell back through the atmosphere and were caught mid-air by planes with long trailing hooks. The technology was barely believable at the time. Cameras capable of resolutions down to a few meters, film magazines that would eject from space, survive fiery re-entry protected by heat shields, deploy parachutes, and be snatched before they sank into the sea. Between 1960 and 1972, more than 100 Corona missions flew, each gathering tens of thousands of images of Soviet missile fields, Chinese test ranges, and the secretive corners of a divided world. For the men and women who pored over those reels in rooms with no windows and heavy locks, the power of such vision was intoxicating and sobering at once. Maps that once relied on rumor and radio intercepts could now be checked against actual photographs. Airfields counted by the number of jets parked in neat rows. Submarine pens traced by their shadows, entire cities measured street by street. The U.S. intelligence community learned quickly that memory was not just a human trait but a strategic weapon. The past, once ephemeral, could now be replayed at will. Leadership in Washington and Moscow began to understand that. What had been seen could not be unseen. Yet secrecy also meant fragility. The film, once analyzed, was stored in classified vaults, cataloged but essentially lost to anyone outside the narrow world of intelligence. Scientists who might have used it for geology, archaeology, or climate study had no idea such a record existed. For decades, the archive grew in silence, a treasure no one outside its keepers could touch. Meanwhile, the satellites themselves evolved. Corona gave way to systems with code names like Gambit and Hexagon. Even sharper eyes that could track cars and tanks, all still hidden behind classification. Then, in a surprising act of openness shaped by the end of the Cold War, the United States chose to release much of Corona's imagery in 1995. President Bill Clinton signed the order. And in a single stroke, 30 years of secret vision spilled into public light. For the first time, historians, environmental scientists, and archaeologists could look back at Earth with a clarity that had never been available. Researchers mapping the retreat of glaciers in the Himalayas suddenly had a starting line, decades older than any civilian satellite. In the Middle East, scholars traced the outlines of lost trade routes and ancient canals buried under shifting sand. In the Arctic and Siberia, geographers compared the extent of permafrost and forest from the 1960s to today's changing climate. Entire cities, once closed to the outside world, appeared as they had been when the Cold War was young. The shock of that declassification revealed how deeply the idea of permanent record had seeped into power, but not yet into culture. Governments had long known that what you capture endures. They used it to check arms treaties, to challenge false claims, to plan and to deter. But for ordinary citizens and scientists, the revelation that a nearly complete visual memory of Earth had been sitting in vaults was breathtaking. It changed how we study the past 50 years, how we imagine the next 50. It also offered an unsettling reminder. Memory, once weaponized, never fully goes back into its box. Every new wave of satellite technology since Corona has been sharper, faster, and digital. The black and white film reels have been replaced by constant streaming data. And while much remains classified, private companies now launch constellations that image the planet daily. Governments are no longer the only archivists. The notion of an empty, unobserved place has almost vanished. Remote valleys, polar shelves, even backyards leave a trail of pixels that can be stored indefinitely. Yet there is also a strange poetry in what the Corona archive became after secrecy faded. Something built to watch enemies now helps us watch our own history and environment. Its grainy frames have been used to map ancient Silk Road settlements, to locate early Maya sites in Guatemala, to trace lost rivers in the Sahara, to reconstruct ecological baselines before human expansion accelerated. Images once meant for generals and presidents now teach students about the fragility of ice sheets and forests. A spy's memory turned into a gift for curiosity. Still, the politics of the permanent linger. The release of Corona was a controlled gesture. Much remains hidden, and new satellites see far beyond what those cameras ever did. As memory becomes easier to gather, questions about who keeps it and why become sharper. The same power that lets us understand glaciers and ruins can also track lives and movements, writing records we may not wish to have. The lesson is double-edged. Memory is power, and power keeps its own ledgers. Standing today before a Corona camera on display at the National Air and Space Museum in Washington, D.C., its massive reels gleaming under lights, one feels both awe and unease. Awe at the ingenuity that turned Cold War fear into an extraordinary archive, and unease at the realization that once the eye opens, it never fully closes. The Earth we thought was passing each day into forgetting has been under watch for more than 60 years. It has been quietly photographed, cataloged, and remembered. In the end, this chapter of human technology fits the larger theme we have been tracing. Nothing is truly lost once the universe, even just our own machines, has taken note. The skies we imagined empty became mirrors, and the photographs they produced outlasted the intentions behind them. Empires shift, alliances fade, but the images remain, waiting for whoever might ask what the world looked like before. Memory, it seems, once captured, serves whomever comes next. Across the modern world, hidden behind fences and featureless concrete shells, there are quiet buildings where the hum of cooling fans and the flicker of cold lights keep the digital present alive. They sit far from city centers, often near rivers that can feed hydroelectric power, or deep in northern latitudes, where outside air helps tame the heat of thousands of servers. These places, sprawling server farms in Oregon's high desert, on the wind-swept plains of Finland, under mountains in Norway, carved into limestone caverns in Kansas, are the memory vaults of our age. Inside them, millions of spinning drives and blinking arrays hold almost everything: emails and bank records, forgotten blogs and abandoned photos, the fleeting thoughts of billions. Yet for all their power and sophistication, they are strangely fragile, and at the same time, disturbingly permanent. It is easy to think of the internet as something airy, a cloud without weight, but its body is physical. Facebook's immense data center at Luleå, Sweden, sits just below the Arctic Circle, feeding on the region's cold air and hydropower. Google runs server campuses in Hamina, Finland, and the Dalles, Oregon. Apple built an enormous facility in Maiden, North Carolina. Each site is engineered like a fortress: thick concrete walls, layers of security, controlled climates that keep temperature and humidity steady so that delicate electronics survive. Yet these fortresses are built for a few decades at most. Their drives fail, their standards change, and the companies that maintain them can vanish. We know because already there are ghost data centers, former hubs of once great networks now standing dark and gutted. Their racks empty, their concrete still warm with memory, and yet the information, the digital fossils, rarely vanish cleanly. Copies persist in backups and caches. Old servers are sold or stored. Tapes and drives are thrown away but not erased. Forgotten corners of the Internet archive themselves without asking permission. The Wayback Machine, a non-profit effort begun in the late 1990s, scrapes and stores pages by the billions, preserving websites long after their creators have died or moved on. Researchers hunting old social networks find fragments still alive on obscure disks or at the edge of search engine caches. Even when a server farm is dismantled, some drives survive in resale markets. And with them photographs, spreadsheets, diaries no one meant to release. Digital forgetting turns out to be harder than it seems. The vulnerability and stubbornness sit side by side. NASA lost track of the original Apollo 11 slow scan tapes. Entire newsrooms have seen archives erased by bankruptcy and failed migrations. Early web communities, GeoCities, Friendster, MySpace, have disappeared with barely a trace. Yet just as often, something you've thought gone lives on. Half-broken but indelible. A tweet embedded in articles long after deletion. A stray photograph on a forgotten image host. An unfinished novel backed up on a cousin's laptop. The Internet was built for resilience, designed by cold war engineers to root around damage, and that resilience means that scraps of our lives linger like pottery shards in the soil. There is a haunting modern echo here of the ruins. Archaeologists uncover in the physical world. When we imagine abandoned digital cities, we think of empty networks, message boards with no new posts since 2007. Multiplayer games whose servers went silent, yet whose landscapes exist frozen on archive disks. Social feeds locked behind login screens no one maintains. These ghost cities are invisible to the eye, but vast in number. And they wait quietly for whoever can still parse their formats. Like ancient Pompeii or Angkor swallowed by jungle, they hold the footprints of ordinary days, conversations about music, recipes, love letters, grief, but now sealed not in ash or stone but in binary. Some corporations build data centers in places that seem almost mythic, as if preparing for eternity. In Svalbard, Norway, a former coal mine now houses the Arctic World Archive. Reels of film and hard drives stored in permafrost, meant to last centuries. Nearby, the Global Seed Vault keeps genetic blueprints of plants safe against disaster. In Nevada, the Long Now Foundation experiments with Rosetta disks. Tiny nickel archives etched with thousands of human languages hidden like time capsules. These efforts reflect a fear we know too well. Our day-to-day memory is fragile, our machines too quick to fail. But they also hint at an ambition to write ourselves into something permanent, to leave fossils for whoever comes after. At the same time, there is something unplanned and wild about our digital past. Unlike carved stone or carefully stored papyrus, data is promiscuous. It copies and leaks. It floats into old backups and forgotten servers. When the social platform Vine shut down, users raced to download their 6-second videos, but countless others still float on mirrors and compilations. When MySpace lost a decade of music files in a botched migration in 2019, some of the songs resurfaced later because anonymous archivists had crawled the site years earlier. These acts of accidental preservation show that the network itself, through its users and redundancies, resists total oblivion. And yet the other side of that resilience is eerie. Our most casual gestures, a text, a photograph, a search, may outlast us in forms we cannot predict or control. Long after a server farm goes dark, its drives might appear on eBay, their platters still whispering of private lives. Long after a website dies, its skeleton remains in scraping tools and academic caches. Digital ruins are already older than we realize. The first web pages from 1991 still load in modern browsers. Their code archaic but legible, like carvings in a cave, to walk through a dark data hall. Silent, except for the echo of old ventilation. would be to feel the scale of this modern archive. Each rack, once bright with status lights, held millions of lives in miniature. And though the lights are out, somewhere those bits are not. This is the new geology. Layers of magnetic domains and flash cells, piled as surely as sediment and fossil bone. We are making our own strata. Future minds, whether human or something beyond us, may study these layers and learn what we loved, feared, and built. Perhaps the most sobering thought is that unlike desert glass or ancient stone, our digital artifacts were never meant to last. Yet some will endure longer than the names attached to them. We do not always choose what becomes permanent. The politics of who controls servers and who unlocks archives will shape the stories told about us. But even if companies close and networks fail, something in the architecture of connectivity, in the relentless copying and catching, means our age will not be silent. These ghost cities and digital fossils will wait in their cold vaults and forgotten nodes. Silent proof that we lived and left traces far beyond what we could hold in our hands, beneath the farmland and vineyards that stretch across the border of Switzerland and France. In a tunnel that loops for 17 miles through chalk and clay, there is a machine built to reach backward in time. It is not a time machine in the way of stories. No one steps inside and emerges in another century. Instead, it uses the most elementary trick nature allows, smashing things together so hard that for the briefest instant, the universe must remember what it once was. This is the Large Hadron Collider at CERN, the European Organization for Nuclear Research. And it is at once the most powerful microscope ever built, and the largest scientific instrument humans have dared to create. When it came online in September of 2008, after decades of planning and construction, it represented a global wager that if we could make protons collide with enough energy, we might coax the earliest chapters of the cosmos to replay themselves and leave us a trace. The principle is deceptively simple. Accelerate beams of protons until they are moving so fast that each carries the energy of a flying mosquito packed into a subatomic speck. Then smash them head-on and watch what flies out. In those collisions, which happen more than 1 billion times per second when the machine is at full power, the energy of motion turns into matter, and for an instant the seething, high-temperature conditions of the first trillionth of a second after the Big Bang return. What emerges is not debris in the ordinary sense, but particles we rarely see in our cold, settled universe, heavy cousins of electrons, quarks shaken from their normal confinement, and, most famously, the elusive Higgs, boson. To do this is not only to build a machine, but to build a memory palace of unprecedented size. Each collision at the LHC creates a storm of data, petabytes upon petabytes every year. Too much for any single nation to store or sift. Vast computing farms at CERN and partner institutions around the world act like an extended nervous system, catching the flashes from detectors the size of apartment blocks. One of these detectors, ATLAs, is a cylindrical cavern of sensors and magnets, 7 stories tall. Another CMS, so massive its sections had to be lowered one by one into a concrete well and then assembled like a ship's hull. When protons meet inside these instruments, thousands of particles spray outward, tracked by layers of silicon and scintillating fiber. The paths curve in magnetic fields, leaving signatures like calligraphy, each telling where and how a bit of the collision's energy condensed into form. All this work, the plumbing of liquid helium cooling the giant superconducting magnets to near absolute zero, the synchronized timing of beams racing around the ring at 99.99999% of the speed of light. The global computing grid of more than 170 data centers is in service of a single, fragile question. What are the fundamental building blocks of reality? And how did they take shape in that first breath of time? In July of 2012, an answer arrived. After 2 years of combing through 400 trillion recorded collisions, physicists from Atlas and CMS stood before the world in a crowded CERN auditorium and announced that they had observed a new particle with a mass of about 125 gigaelectronvolts, fitting the long-sought profile of the Higgs boson. Its discovery confirmed the mechanism that endows elementary particles with mass. An idea first put forward by Peter, Higgs and others in 1964 when the Standard Model was still being built, for half a century. The Higgs was a missing entry in physics ledger, a predicted but invisible piece needed to make the equations whole. Without it, the universe's particles would have remained weightless and structureless. Atoms, stars, and life itself could not form. Its eventual sighting was not just a triumph of engineering and patience, but a kind of unlocking proof that by recreating a sliver of the Big Bang, could coax out a truth hidden since the dawn of time. The announcement's images, Peter Higgs himself, elderly and moved to tears in the auditorium as the plots flashed on the screen, carried the quiet emotion of a lifetime's pursuit fulfilled. Yet, the LHC's work is larger than one discovery. Each dataset it collects is a map of what is possible in the deep fabric of reality. Even when nothing new appears, the absence itself is a record, closing doors on theories, narrowing the guesses about what lies beyond the Standard Model, supersymmetry, dark matter candidates. Extra dimensions all have been tested and constrained by the machine's quiet, relentless witnessing. Its archive is not just bits, but a collective memory of human effort to question the very beginning. The way that archive is handled is as intricate as the collisions themselves. Data from the LHC travels along dedicated optical lines to CERN's servers, then outward to a global grid that includes universities and laboratories on every continent. Copies are stored in multiple places. Redundant tapes and disks keep raw and processed events alive for decades. Students in São Paulo and Warsaw analyze the same bits captured under Geneva farmland. A collision lasting less than a trillionth of a second may live in analysis forever. There is an irony in this. To explore impermanence, the fleeting instant when energy condenses into matter and then vanishes again. We build machines and data systems designed for longevity. We act as stewards for a cosmic diary we do not yet know how to read completely. The LHC's billions of events, each tagged with time, position, momentum, and charge, are a way of freezing the fire of creation. Long enough for slow human minds to approach it, walking through CERN's surface campus. With its 1960s concrete and its newer glass-walled control rooms, you would not immediately guess that below your feet an immense loop hums with such purpose. Yet inside the ring, protons whisper of what the universe remembers about its own birth. When we speak of colliders and clues, we are really talking about forcing the cosmos to show its old photographs, kept in the rules of quantum fields since before any star burned. The Higgs boson was one such photograph, pulled from the blur of collisions like a long-lost family portrait. Others may come, and even if the next discoveries take decades, the machine's record already stands, a patient, organized echo of the first light and the first matter, proving again that the past never wholly disappears in quiet laboratories scattered across the world, where dilution refrigerators hum like distant bees and cables snake into sealed steel chambers colder than interstellar space. A new chapter in the story of memory is being written. It is a chapter so small it can barely be pictured. Not cells or circuits, but the dance of single quantum states. Electrons and photons and superconducting loops balanced on the edge of knowability. The dream is to build machines that can remember and calculate using the same strange rules that make the quantum world so puzzling. These are quantum computers, and though they are still young and fragile, their arrival has already begun to alter how we think about information itself and what it means to hold a record, safe against time. Ordinary computers store data as bits, each either a 0 or a 1, each stable enough to keep its value unless something goes wrong. But quantum bits, or qubits, are built to hold richer, more delicate states. They can be 0 and 1 at once, in a superposition that lets them explore many possibilities at the same time. They can be entangled with one another so that changing one instantly shapes the other, even across distance. This ability, if controlled, could let quantum computers tackle tasks that would overwhelm any machine built from classical bits. Yet it also makes them almost absurdly sensitive. A stray vibration, a flicker of heat, a cosmic ray hitting a chip. Any of these can collapse the fragile state and wipe the memory before it is used. For decades, this fragility seemed an impossible barrier. But slowly, step by careful step, physicists and engineers have learned to protect and correct quantum information. They cool qubits to millikelvin temperatures where noise slows and organize them in arrays so that groups of qubits watch one another for errors. In 1995, Peter Shor proposed a method for quantum error correction that seemed nearly magical, encoding one logical qubit into a set of several physical qubits. You could detect and undo mistakes without ever looking directly at the quantum state and destroying it. Since then, new codes have followed. Surface codes. Color codes, each a clever way of using entanglement itself to guard against the world's interference. In recent years, these ideas have left blackboards and become experiments. Google's Sycamore processor, IBM's superconducting qubits, ion Qs, trapped ions, and rigs in Delft and at Yale have all demonstrated small but real error-corrected steps. In 2023, researchers at Google and Harvard reported extending the lifetime of a logical qubit beyond that of any single physical qubit, sign that true quantum memory may be achievable. Each advance is another quiet victory in the race to make these ghost-like bits durable enough to be useful. The stakes are not limited to faster computing. If we can reliably store and manipulate quantum states, we gain new tools for protecting and unlocking secrets. Quantum cryptography uses entanglement to create keys that cannot be copied or intercepted without detection. Quantum networks might one day span continents, sharing information in ways immune to eavesdropping. Old cryptographic systems, built on the hardness of factoring large numbers, could be broken by sufficiently powerful quantum machines, reshaping how governments and companies guard their archives. Memory becomes a field of security as much as science. There is also a subtler promise that touches the heart of time itself. Quantum systems are exquisitely sensitive to phase and coherence. They act like tiny clocks, aware of intervals beyond the reach of any mechanical pendulum. By controlling quantum memory, we could build clocks that barely drift across the lifetime of the universe. Instruments so exact, they might measure the expansion of space or detect tremors in the fabric of time caused by gravity, waves, and unknown physics. Some theorists imagine using entangled particles to probe the very limits of relativity, to test whether time is as smooth and shared as Einstein described, or if there are deeper quantum grains beneath it. Yet the quest to master quantum memory is also a meditation on forgetting. Nature resists long-lived superposition. It wants to scatter and decohere, to mix states until the simple quantum story becomes complex and classical. Each step toward error correction is a fight against that tide. The machines built to house qubits, dilution refrigerators towering like silver trees, shielded rooms lined with mu metal to block magnetic fields, endless cables carrying microwave pulses are all acts of defiance against entropy's drift. They are humans, patient and stubborn, trying to coax permanence from the most ephemeral substrate. If they succeed, the implications could echo far beyond laboratories. Weather prediction, molecular design, fundamental physics, secure communication, all might be transformed. We might store patterns of quantum information for years or centuries, like delicate butterflies pinned in glass, but still alive. We might run computations that replay the birth of the cosmos with a clarity beyond current reach. The very question of whether the universe forgets could shift once we can keep a quantum diary of our own. But there is caution in the dream as well. The same permanence that protects can expose. If quantum machines one day crack old encryption, the secrets of decades past might surface. Banks, states, and private lives are entangled with mathematics once thought safe forever. Memory, once tamed at this level, cannot be unlearned. It will remake what privacy means. Still, the effort continues, with a sense of wonder as well as caution. Walk through a quantum lab at MIT or Delft, and you see tables crowded with lasers, mirrors, and cryogenic tanks. You hear the low whir of pumps. You feel the meticulous care of researchers who know that a single stray photon could undo hours of work. Their aim is simple to state and monumental to achieve. Make a qubit remember itself long enough for us to ask it hard questions. Each extra microsecond of coherence is celebrated. Each successful correction a hint that we are bending the raw fabric of chance towards stability. We have spent centuries expanding the scale of our memory, from clay tablets to libraries, to magnetic tape to planetary networks of data. Now the frontier runs inward, to the smallest possible records, to memory stored in the spin of an electron or the gentle vibration of an ion. If we can hold these states, if we can keep them safe against the chaos of the world, we will not only compute differently, we will know differently. We will have reached a place where the most fleeting whisper of the quantum can become durable, where the pale ink of the future is written at the tiniest scale, and may one day let us read back through time itself with a clarity we have never known. Deep inside the human skull, beneath the fragile bone and protective layers of membrane, there is a landscape so complex that even after more than a century of mapping and measuring, scientists cannot fully explain how it turns fleeting experience into the quiet permanence of memory. Billions of neurons branch and connect, exchanging signals with electrical pulses and tiny chemical messengers. This network is astonishing in its scale and intricacy. Yet for some researchers, it is still not enough. They look at the brain's shimmering patterns of activity and wonder whether something even stranger might be taking place, something that touches the deep, unsettled world of quantum physics. These speculations have given rise to one of the most intriguing and controversial ideas in modern science, that consciousness and memory might depend not only on synapses and classical networks, but on delicate quantum processes inside the cells themselves. For decades, the mainstream explanation has focused on the synapse, the microscopic gaps where neurons meet and talk. Each time we learn, the strength of certain connections changes. New spines sprout, old ones weaken. Long-term potentiation, first described clearly in the hippocampus of rabbits in 1973, shows how repeated firing makes a pathway more efficient. A simple mechanism that can account for many aspects of learning. Chemical cascades reinforce the signal. Proteins shift to make future transmission easier. In this view, memory is a story of wiring and rewiring. Physical and robust, yet also flexible enough to adapt. But in the early 1990s, the English mathematician and physicist Roger Penrose and the American anesthesiologist Stuart Hameroff proposed something far bolder. Penrose, whose work on black holes and singularities had already reshaped physics, argued that human understanding and creativity seemed to escape the limits of purely algorithmic computation. Hameroff, who studied how anesthetics shut down awareness, pointed to structures called microtubules, tiny cylindrical scaffolds, inside neurons that help maintain their shape and guide molecular traffic. Together, they suggested a model they called orchestrated objective reduction, or ORCOR. The idea was that microtubules could support coherent quantum states, brief but meaningful patterns of superposition that, when they collapsed into definite states, might produce moments of conscious experience. These collapses, happening in orchestrated waves across networks of neurons, would not only generate awareness, but also encode memory in ways classical synapses alone could not explain. The response from most neuroscientists and many physicists was skeptical, even dismissive. The brain is warm and wet, full of thermal noise that should destroy quantum coherence almost instantly. The calculations suggested that any delicate quantum state would vanish in trillionths of a second, far shorter than the millisecond rhythms of neural activity. Critics pointed out that while microtubules are fascinating cellular structures, there was little evidence they could behave like quantum computers. To most, consciousness remained better explained by the known, if incomplete, principles of network dynamics, yet ORCOR has refused to die. Partly this is because Penrose and Hameroff have continued to refine their arguments, and partly it is because mainstream neuroscience still cannot close all the gaps. How exactly subjective experience emerges from firing neurons, the so-called hard problem of consciousness, remains unsolved. Memory, too, has mysteries. People recover long-buried details decades later, sometimes after brain injury. Smells or sounds can trigger whole scenes. And the durability of certain memories over a lifetime is difficult to reconcile with constant cellular turnover. These puzzles have left room for speculation. Over the years, some experimental hints have encouraged curiosity, if not full belief. In 2014, researchers at the University of California, Santa Barbara reported fleeting quantum coherence in photosynthetic systems at room temperature, showing that warm biological structures might sustain delicate quantum effects longer than once thought. Others have noted that microtubules have regular lattice and could, in theory, support wave-like phenomena. In 2020, teams using extremely sensitive magnetic detection in rodents suggested that some brain processes might produce faint quantum-like signatures, though the interpretation remains uncertain and controversial. Meanwhile, quantum-inspired metaphors have seeped into popular culture and serious theory alike. Books by Penrose such as Shadows of the Mind, 1994, and Hameroff's decades of talks have kept the idea alive. While philosophers of mind debate whether physicalism, the idea that everything about the mind is explainable by known physics, needs revision. Even if Orcor itself is never proven, the broader question it raises persists. Might consciousness and memory require a deeper physical description than neurons exchanging chemicals? At the same time, practical neuroscience marches on, building brain-computer interfaces, decoding speech from neural activity, mapping memory circuits with optogenetics and fMRI. Each advance shows that a great deal of mind and memory can be explained without resorting to quantum mysteries. Still, the seduction of the unknown lingers. Some researchers say that even if the brain does not exploit quantum coherence for computation, it could still be subtly influenced by quantum effects in ways we do not yet measure. Synaptic molecules are quantum objects after all, and their stochastic behavior may not be purely classical. The persistence of these speculations speaks to something deeper than data. Consciousness feels unlike any other physical process we know, and memory feels impossibly rich. It is easy to imagine that something beyond circuits and chemistry is at play, especially when physics itself teaches us that the world's bedrock is not solid but probabilistic. A sea of possibilities until observed. The mind, being the thing that observes, seems poised on the edge of that mystery. Perhaps in the end, the value of these quantum brain hypotheses is less about proving a specific mechanism and more about refusing to let easy answers settle too soon. Penrose and Hameroff may be wrong about microtubules as quantum processors, but their challenge keeps the field alive to deeper possibilities. It reminds us that memory is not just a list of stored files. It is the vivid reassembly of experience from living matter. Matter that, at its heart, follows rules stranger than any story. In the quiet rooms where neuroscientists work, labs at Arizona, where Hameroff teaches, lecture halls at Oxford, where Penrose still occasionally appears, the conversation continues. It is not a debate about gadgets, but about the fundamental nature of reality and mind. Whether the brain is a quantum echo chamber or simply a vast classical network, the hunger to understand its memory will not end. And in that hunger is a kind of poetry. The very thing asking the question is the organ trying to remember itself, to learn how it keeps the past alive long enough to dream of the future, far beyond the planets, where sunlight thins and the solar wind weakens into the pale breath of interstellar space. Two small spacecraft drift slowly outward, carrying messages from a species that has only just begun to understand its place. Voyager 1 and Voyager 2, launched in 1977, are no longer sending sharp images of moons or magnetic readings from Saturn. They are now silent scribes, each bearing a golden record etched with sounds and greetings and music meant for no one in particular. Decades after their flybys, they still move outward at more than 30,000 miles per hour. Tiny sparks from Cape Canaveral, now more than 20 billion kilometers away. They are not fast enough ever to escape the galaxy, but they are fast enough to leave behind our sun's direct sway. In doing so, they have become physical proof that humanity adds its line to the great, unrolling scroll of spacetime. Even if no one listens, even if no one finds them, the act of sending is itself an entry. And yet the scale they sail into dwarfs everything we can picture. Cosmologists speak of the cosmic horizon, the farthest distance from which light has had time to reach us since the Big Bang. About 46 billion light-years in every direction. We are surrounded by that edge, not as a wall, but as a limit. Beyond it, space expands faster than light can bridge. So events occurring out there will never be known to us. During the first fraction of a second after the universe began, a period called inflation caused space to balloon unimaginably fast, stretching tiny fluctuations into vast swaths of sky. Some regions sped away so quickly that their light is forever beyond our reach. We will never see them, never know what galaxies or histories unfolded there. And yet in the mathematics of cosmology, those unreachable regions are not gone. They remain part of the same spacetime, connected to us in origin and encoded indirectly in what we can observe. This idea that the observable universe carries fingerprints of the unobservable is both humbling and hopeful. The cosmic microwave background. The faint afterglow of the Big Bang, discovered accidentally in 1965 by Arnaud, Penzias, and Robert Wilson when their Bell Labs antenna picked up a persistent hiss, is one such fingerprint. Its delicate modeling, mapped with exquisite detail by satellites like COBE in 1989, WMAP in 2001, and Planck in 2009, shows tiny temperature differences. Seeds of structure left behind by inflation. Those patterns are statistical whispers from realms we will never touch. The way space stretched and cooled is written there, giving us a ghostly map of events forever out of reach. In this sense, even what cannot be visited or returned to has left a record we can read against such immensity. The Voyager probes seem almost comic in their fragility, yet they are profound because they embody the same principle at our human scale. When Carl Sagan and his team designed the Golden Records, with Chuck Berry's Johnny Be Good, greetings in 55 languages, and sounds of Earth's rain and heartbeats, they knew the odds of anyone finding them were almost zero. The message was partly for us, a declaration that we existed, that we could think across gulfs of time. The records, protected by gold and carefully etched to survive perhaps 1 billion years, are a human echo tossed into the dark. Even if they drift unplayed forever, they are already part of the cosmic story. They have altered the state of matter and energy. Their signal has left Earth and is still expanding at light speed in faint radio waves, adding our small murmur to the grand background. New Horizons. Launched in 2006 and famous for its 2015 flyby of Pluto, now follows a similar path, carrying digital inscriptions and a small aluminum token stamped with the images of Clyde, Tombaw's ashes, and the craft's schematics. It too will eventually slip beyond the Kuiper Belt and sail outward, another ambassador of our need to be known. As these craft fade into the long night, they join countless other silent artifacts, the early TV broadcasts leaking from our planet since the 1930s, the radar pings from Cold War experiments, the pulses of Arecibo's Great Dish aimed at star clusters. None of these signals can be recalled. Once loosed, they become permanent faint ripples on the electromagnetic sea. This realization changes how we think about endings. We often speak as though events vanish when forgotten, but physics does not support that wish. The expansion of space may hide regions forever, but their early influence is still here. Our own acts may seem ephemeral. A radio show in 1941, a web post in 2024, yet those bits have left. Earthen will travel until absorbed by dust or bent by gravity into new shapes. Every transmission is a kind of Voyager. The cosmic horizon also forces a different kind of humility. We live inside a bubble of knowable history. Outside, the universe writes without us, but that boundary is not empty. It is the reason our sky looks as it does, the reason galaxies cluster the way they do. And just as we deduce lost civilizations from ruins, we deduce lost regions from these subtle signatures. The idea that inflation-stretched space means the farthest galaxies we can see are but a fraction of what exists. Beyond them, countless other stories play out, never to touch us yet joined by origin. That connection, invisible but mathematical, is a memory of shared birth. So when we build machines to cross the solar boundary, we are mimicking a deeper truth. The universe is already an archive, but we long to leave our footnote inside it. Our probes are not explorers in the usual sense. They are ink. The golden record's grooves are no different in principle than the ripples inflation left on the microwave sky, just smaller, more personal. They say, "We were here, we knew enough to try." Perhaps in 1,000,000,000,000 years. When the Milky Way and Andromeda have merged, and the night sky is strange beyond recognition, some shard of those records might still drift among alien stars, unread but real. Perhaps no one will remain to decode Planck's maps or Voyager's songs, yet the patterns will persist, faint but indelible. The future's pale ink is not bright or loud. It is quiet scratches on spacetime, whether carved by cosmic birth or by a small, determined species reaching beyond its cradle. To stand under the night sky knowing this is to feel a deep, strange kinship with the void. We cannot outlast the horizon or reclaim the unreachable, but we can add our own line before the page turns. That line, once written, joins the record kept by physics itself. And in that sense, we are already part of a map without end. In the end, after the black holes and cosmic rays, the frozen deserts and the data vaults, the idea turns and comes home. It is no longer about distant telescopes or colliders humming under the soil of Europe. It's no longer about satellites falling into the dark with gold-plated records. It is about the simple fact that each of us, without trying, is already part of the record. A breath taken on an autumn street moves air that will never again be quite the same. The warmth from a hand on a railing enters the restless drift of molecules. A thought sparks and sets off a chemical pulse that rearranges matter forever. We live as if most of what we do is lost to time, but physics does not agree. Every action changes the world in ways that cannot be perfectly undone. We are written whether or not we sign our names. To feel this is at first unsettling. If every step and word leaves an indelible trace, then our lives are not the private, evaporating events we sometimes imagine. The body itself is an emitter, infrared light, faint electromagnetic noise, particles of breath and skin. Long after a conversation ends, bits of it are in the air and the walls, and the world's molecules have been slightly retuned by its passage. The grand scale's cosmic microwave maps, event horizons, show this principle with beauty, but it also holds in a kitchen or a city bus. Memory is not only human, it is the quiet bookkeeping of matter. Ethics begins to feel heavier when seen through this lens. We know our choices affect people, but here the idea stretches further. There is no complete forgetting. Harm leaves scars beyond recollection. Kindness leaves warmth beyond witness. Even if no one remembers a good act, the world's order is altered by it, however small, however hidden. The glass is fused, the dust shifted, the molecules of breath stirred. Some may call that poetic rather than scientific. But it fits the grain of physics. No event is perfectly reversible, no signal perfectly erased. In that sense, each life is a permanent experiment, contributing to a story we will never fully read. Yet there is humility and comfort here as well. Many people fear that what they do will vanish, that lives without monuments dissolve into nothing. But the universe itself will not allow absolute erasure. The tea cooling on the table, the footfall in the snow, the warmth passed from one hand to another, each is already woven into the larger unfolding, faint but real. Our stories may not be carved in stone or stored in some library, but they are inscribed in fields and particles and distant photons still on their way outward. When we step back and see this, wonder follows. The same physics that tracks galaxies and guards the memory of the Big Bang also holds the tiny moments of ordinary days. A smile to a stranger, a letter burned in anger, a melody hummed alone, each rearranges something physical. And that rearrangement cannot be wholly undone. To know this is not to be paralyzed, but to be awake. It is to understand that presence is more consequential than it appears, that even in anonymity, we are making marks. There is also release in recognizing how small and diffuse those marks are. We do not control what the universe does with them. They scatter and mingle with billions of other traces, folded into weather and light and new beginnings. Our job is not to curate the grand archive, but to live carefully within it. knowing that nothing is wasted, but also that nothing is entirely ours to keep. Philosophers long try to comfort us about meaning. Physicists rarely enter that territory, yet their findings push us toward it anyway. The arrow of time, the persistence of information, the impossibility of perfect forgetting. These are as close to a metaphysics as science will allow. They say, your life is already recorded in the deepest way matter records. You may not read the book, but it is being written. And it is not a book of judgment, but of existence itself. There is a gentleness in seeing our smallness inside something so vast. Voyager's faint radio whisper, drifting for 47 years and counting. It's just a louder version of what every heart and breath does each day. We do not need to launch probes to join the cosmic diary. We are already in it. The question becomes less whether we will be remembered and more how we wish to spend the time of our writing in that light. The quiet reckoning is not frightening but clarifying. If everything persists in some way, if even our forgetting becomes a kind of record, then attention matters. To pause, to choose, to create, to heal, these become ways of shaping what cannot be erased. To harm thoughtlessly is to seed pain in places we will never see. To help without reward is to scatter resilience into the same invisible ledger. And so the story that began with block universes and black, whole paradoxes, with glass and desserts and muon shadows and pyramids, arrives not at equations but at a simple awareness. We are part of the archive we wondered about. Spacetime itself, vast and silent, is the library. Each of us is a sentence being added, looking up at the night sky. One might think of all the things thought lost, the words unsaid, the kindness unnoticed, the lives unlabeled. Yet above and beneath and within, the universe is keeping them, not to display or punish, but simply because that is what reality does. It remembers. The weight of that fact is quiet but steady. It can frighten or console, but either way it frees us from the illusion that we are shadows passing through nothing. We walk. We breathe, we think, and those acts ripple outward into a memory larger than time. A record no one owns, but everyone joins. To live knowing this is to live with wonder and humility. Wonder at the reach of even our smallest motions, and humility before a cosmos that holds all of it, patient and unhurried, writing without pause.